Welcome to Real Chemistry. I'm Dr. Morris, and today we're going to learn how to use an integral key. If you look down below, what you'll see is a list of formulas that help you solve integrals you don't know how to do. Now, there may not be the exact function down here that you want to solve, and that's okay. If you go to Wikipedia, you can find a giant list of integrals you can do. Let's go ahead and use one of these keys to solve an integral. Alright, so here I have the function 6 pi over 1 plus cosine 2 n pi x. How am I going to solve that guy? Well, this turns out to be pretty tough to do with methods you might have learned in calculus. So let's go ahead and use an integral key. What are the steps to do that? Well, step 1 just says write the integral and remove the constants. And so what we're going to do is we're just going to go ahead and write this as an integral. And notice the 6 pi can be pulled out front because it's just a constant. 1 plus cosine 2 n pi x. We can't pull out the constants in the cosine because they're in the argument of a function. And this is going to give us this integral, which now what we need to do is go find something that looks like that, and that's step 2. So step 2 just says identify the correct integral key. And we want to find something of the same functional form. And there's such a long list of integrals that this can sometimes be the most challenging part of the problem. So what you want to do is make sure you understand what type of function you're dealing with. And here we're dealing with a trig function. So if you go to the list of trig functions and you look for one with cosine in the denominator, that'll be a good start. And you can see down here that we have 3 with cosine in the denominator. Now, this top one has 1 plus cosine, so that looks good, but let's look at the other two also. This one has 1 minus cosine, so that one doesn't match because there's a minus there where we have a plus. And the bottom one has an x up top, so that one doesn't match. So the one that we're going to use is this top guy up here. So, what's the next step? Well, now we want to identify the value of the constants. If you look through our integral key, you'll see that they have a constant somewhere in their equation, and we may not have that same constant, and that's okay. This is just a formula, right? So here you'll see that we have an a in front of the x for our cosine. And we need to identify what that a is. So that's step 3, and all we're going to do is we're going to say, okay, where I see the a, I'm going to underline in my formula. So I see the a right there. And that tells us that a is going to be 2 n pi. Sometimes it's not as easy as this to see. So a trick is you can always say, okay, well, I know here we have ax written, so I'm going to set that equal to whatever is all in my cosine, 2n pi x. And then we can see that my x's are going to drop out, and that'll just leave us with a equals 2n pi. Maybe not necessary in this problem, but in some harder problems, it's nicer to write it out that way. All right, and now step 4, write the solution, and that's why integral tables are so nice. Here is our solution over here, and all we're going to do now is write out that part of our integral key, only we're going to, every time we see a, we're going to replace it with what we just found to be a. So that means our integral is equal to 1 over a, we see this a down there, and our a we know is 2 n pi. And then it's going to be times tangent, and we have a, and our a, once again, we know is 2 n pi, so we're not going to write a, we're going to write 2 n pi. And then we see that they have an x in their argument of tangent, and that it's all over 2. So we're going to write over 2. And then finally, since this is an indefinite integral, we're going to remember to write the plus c. Okay, we can simplify that a little bit. Our 2's cancel out in the argument of our tangent, and that can give us 1 over 2 n pi tangent n pi x plus c. And that's our integral. So you can see that it might take a little practice to use the integral keys. Once you have them down, it's an easy way to do an integral. Let's take a look at one more. Here we have an exponential function. And so if you want to try to find this argument or this function, you're going to want to look in the exponential section of an integral key. We know it's an exponential because we see that e. Now, further, this is a definite integral. It says determine the definite integral from negative infinity to positive infinity. And so that's going to change a little bit about what we do here. So what we're going to want to do is go ahead and identify still what function this matches with. And then we'll use some tricks here in a second. So this guy is e to the negative 3n x squared over 2. And so what we're looking for is we need an x squared and we need this negative sign. And if we look down at our integral keys down here, we'll see that this one right here is e to the negative x squared. So that's a good sign. That means that we can use that one to solve our integral. So let's go ahead and write down our integral. We're going to get the integral from negative infinity to positive infinity, because that's the bounds it gives us, of 4e to the negative 3n x squared over 2 dx. That's what we want to solve. We want to know, what does that equal? Well, here's where a math trick comes in. Because if you notice, the bounds in our integral key are from 0 to infinity. And the bounds that we want to solve for are from negative infinity to positive infinity. So what do? Well, here's where a math trick comes in handy. And that is, for odd functions, the integral from negative b to positive b is always equal to 0. And for even functions, the integral from negative b to positive b is always equal to 2 times that same integral, only now we replace the bottom bound down here with a 0 instead of a b. And if you want more information on how to identify odd and even functions, or how to understand why this is true, I'll link to 2 math videos that are pretty good that'll explain this in more detail. But let's think about what that lets us do. That means that we can go ahead and rewrite our integral as 2 times the integral from 0 to positive infinity. Why? Because this turns out to be an even function. Notice that it's x squared, and that's actually what makes it an even function. And so that means that for our even function, we can write it as 2 times 0 to infinity, and then we write our same function, 4e negative 3n x squared over 2. All right, so now we've gone ahead and used the fact that it's an even function to rewrite it in a way that matches our integral table, and that's something you might have to do from time to time. All right, now let's go ahead and remove the constant. So basically we're at step 2. And you'll notice here that we see this 4, and that's just a constant in front of our function. So we're going to pull that out, and we're going to say 8, because 4 times our 2 up there gives us 8. Our integral is from 0 to positive infinity. Let's write it neater, infinity. And then we're going to be left still with our function, which is e to the negative 3n x squared all over 2 dx. And we want to know, okay, well, now let's identify the correct integral key. We've already said we want to use the second one. And now we need to identify the constants. We want to know, what is this a in there? And this time it's really going to be a lot easier to go ahead and say, okay, a times x squared, negative ax squared, which is the argument you see right here in the exponential, must be equal to the argument we have in our exponential, negative 3nx squared over 2. Notice that I've taken the argument in our exponential and just set it equal to the argument in the integral key's exponential. So what does that tell us? That tells us, well, our x squareds are going to drop out, and so is our negative 1. And so that tells us that our a then is equal to 3n over 2. All right, let's go ahead and solve this now. That's step 4, write the solution. All right, so this is going to be equal to, we still have our 8, and then we're going to go ahead and brackets, write out the other half of that integral key. That's the answer side, right? So it tells us it's equal to 1/2 times a square root, that's the second part, of pi on top and whatever we got for a on the bottom, which is 3n over 2. So that's our answer. It looks a little ugly right now, so let's go ahead and simplify that. We can multiply the 8 by the 1/2. And when we multiply the 8 by the 1/2, we're just going to get 4. And then we can go ahead and multiply by the reciprocal of this fraction down here. You don't want to leave a fraction in the bottom. So we multiply by the reciprocal of that, and that's going to bring the 2 up top and give us 2 pi over 3n. So that's the answer. Notice there's no plus c because this is a definite integral. So you can see that using integral keys can range from really straightforward to a little more complicated. This is just 2 examples. If you have any questions about how we did that, please ask them below. Also, go ahead and subscribe to Real Chemistry by clicking on that icon down below, and you can also check out another video to my left. Thanks for watching.